So far we've been looking at changes in gases or other systems just in terms of conservation laws, conservation of momentum and conservation of energy primarily. And in each of those laws, really the only requirement is that the final and the initial state have to have an equal sum. And so the final states and the initial states, they don't really have anything distinguishing them in those situations. So we might think from those that any process, as long as energy and momentum are conserved, any process is equally likely to happen. So if I think about something like a car crash, a car runs into a brick wall, and we get this change in energy, where we had kinetic energy in the car, and then it runs into the brick wall, and that energy is changed into thermal energy as it bends the metal, and it causes the deformation of the metal, and so that's elastic potential energy, and some bits of the car are going to go flying off, and there's kinetic energy for those, and they might go flying up into the air. There's gravitational potential energy. It makes a big sound, so we've got some vibration in the air molecules there, and so we might think that it's just as likely then, since it would still follow the conservation of energy law, for this wrecked car to suddenly reform, all the pieces come back together, the metal unbends, and the car starts to move back in the direction it came at the original speed. That doesn't violate the conservation of energy or the conservation of momentum ideas, but it doesn't happen. So this gives us the idea that there must be something else going on, some other law that we haven't talked about that governs the direction of these processes. And so this is this law we call the second law of thermodynamics, and it's talking about entropy. So entropy, before we get into the second law, entropy is a measure of the disorder of a system, or the probability of a particular arrangement of a system. So if we look at these two systems, in this one we have all of our little atoms that make up this object. They're arranged in this nice, tight little grid, and everything has its place there, and everything's right on the intersection of the grid there. Over here, there's no noticeable pattern to it. You got some that are on the grid lines and some that are between them. Some areas that are a little heavy on the dots. We've got a lot of dots right here. Some that are pretty sparse on the dots. They're right here. There's not much uniformity here. Well, it turns out that situations like this are really common. There are a lot of ways to arrange these atoms that aren't orderly. And there's very few ways to arrange atoms that are orderly. So if we have a system where there's lots of little pieces that are moving around and they're bouncing off of each other, it's far more likely that we'll end up with a system that's very much disordered than a system that has a lot of order to it. So there's a strong likelihood of some kind of a disorderly situation. It doesn't have to be this exact one, but anything where there's no pattern, that's really a lot more likely than one where we do have this clear-cut pattern. Everything has its place. So the second law of thermodynamics just says that entropy, or the disorder of a system, entropy always increases in a closed system. Okay, so if we don't interfere from the outside, if we don't take our little tweezers from the outside and our atomic tweezers and start moving these atoms around to get them on the grid, then the odds are so small of these atoms moving to arrange themselves like this one that we might as well say that there is zero. Not just 1 in 1,000, not just 1 in 1,000,000, but 1 in a nearly infinite number there. So basically the odds are zero of this happening. Another example people talk about is if you're sitting in a room that's filled up with air, all these little air molecules are bouncing around like crazy, there is some probability that at one moment in time, all the air molecules will just happen to be lined up so they're all moving in the same direction and they completely evacuate half of the room. All the air molecules occupy only one half of your room. But it's so unlikely that that would happen that we say the probability is almost zero, basically zero. We treat it as though it's zero. So entropy always increases in a closed system. So if we took that room, we divided it, and we put up plastic between the two halves of the room, we totally evacuated the air from one side of the room, and we'll just assume that we have a really good seal and we're able to get all the air out, so the air is really able, really just on one side of the room there. And then we cut the sheet, or we cut the plastic between the two areas, then very quickly we'll see that air is going to spread into the other half of the room, and we get this disorderly system. Again, unless we do some active work to organize that air. We get our vacuum pump out and we start pumping it out of one half of the room and into the other half. If we think of a ball that's falling, and let's say that it's a ball that's really cold, so there's not very much motion of the atoms here. They're basically held in place, just a tiny, tiny bit of wiggling of these atoms. And we look at this ball falling, then each one of these atoms has a velocity in roughly the same direction, a small amount of variation here. When that ball hits the ground, and we'll say it's not a bouncy ball, so it's just going to hit the ground and lie there. As soon as it hits the ground, well, the atoms in the ground, they're going to be colliding with the atoms in the ball, and they're sending them off in a variety of different directions, and they make them move a lot more than they were, at least some degree more than they were before. So we have more thermal energy here, more movement of these atoms. And that movement is going to be in all different directions here. Now that's a fairly likely state, that our movement would be in a variety of different directions. It's very, very unlikely, so unlikely we'll say it can't happen, for all of these atoms to spontaneously start moving in the upward direction and our ball just to jump up into the air. So the second law says that in a closed system, entropy always increases. So if we want to decrease entropy, we have to do some amount of work in order to make that happen. And then entropy can stay consistent from one moment to another if the disorder of that system doesn't change. And in order to do that, well, entropy always increases in a closed system. So we probably have to do maintain some special circumstances in order to keep that entropy at a constant value.